Okay, here is my video about difference of two squares. Okay, and what difference of two squares is? There are factoring problems that take a sort of pattern. We've learned how to factor trinomials. We did it with our box method. And so if you see one that takes a form like this, where it's a square number and a square number, and they're being subtracted, that's the difference of two squares. And these type of problems have a certain pattern in factoring so that we don't have to do our full box method every time. And so let me look at this for example. These are both square numbers because x times x is x squared and 3 times 3 is 9. So they're both square numbers and they're being subtracted, so that's why it's the difference of two squares. Now let's just do this with our traditional box method just so that we can see the pattern, and then once we see the pattern we won't have to do the box method every time. I know that the term that we're missing here is our first degree term. In other words, our x term is not in this polynomial. So I could rewrite this binomial like this with 0x, because having 0x is the same as not even having it at all. And so if I do that, I know that my x squared term goes in the top left box and my negative 9 goes in the bottom right. And so I'm looking for values that will multiply to give me negative 9x squared, but those same two values, when I add them, will give me 0x. Well, we know if they add to give you 0, then those are those equal but opposite values, such as 3x and negative 3x, or 8 and negative 8. Values that would cancel each other out. And so by looking at this, I know that they're equal but opposite, and they have to multiply to give me negative 9x squared. So hopefully you've kind of figured out that our values are negative 3x and 3x. And we know that it doesn't matter which one goes where. Negative 3x or negative 3x can go in either box, so I'm just going to pick one. I'll put negative 3x there and 3x there. And then we're factoring out our GCF. So the GCF of those is 3. The GCF of those is x. And if I find the GCF up, the GCF of those is x. And the GCF of those is negative 3. Because that box is negative, I'm using a negative. And I see that these are the factors that I've gotten from my box method. X plus 3 times x minus 3. And you could always distribute this back out to check it and make sure it ends up being equal to our original binomial. But you see the pattern here. And what we have is I have in each of my two parentheses, I got the square root of the first term plus the square root of my second term times the square root of the first term minus the square root of my second term. So in other words, the pattern, and we could do this for 20 different problems so that you could see that the pattern's true for all of them, or you could just trust me. But what we have is that if you have the difference of two squares, I can factor that by saying the square root of the first plus the second times the square root of the first minus the second. This is my difference of two squares pattern, and I want you to get to where if you see this, boom, we can just write that. I don't have to do this box method every time because this pattern is always true. So what we have is, I'll zoom out so you can see the notes up top, but I've got 3 additional problems. So what you may want to do now is you may want to pause the video and work through these and then hit play to check your work. But in case you don't want to do that, I'm going to go ahead. And so what we have here is, if I'm going to follow this pattern, I know I've got the square root of the first term plus the square root of the second term times the square root of my first term minus the square root of my second term. And as always, I can multiply this back out to make sure it works. Let's go and do that on this one. Y times y is y squared. Y times negative 5 is negative 5y. 5 times y is 5y. And 5 times negative 5 is negative 25. Since those cancel, I end up with my original polynomial, and that's how we know that our factors are correct. So once again, if you got this, you're correct. Now let's look at the second one. This one's a little bit trickier because my squared term is not just a variable squared, it's got a coefficient as well. But I know that the square root of 9z squared is going to be 3, and then the square root of z squared is z. And that's going to be plus the square root of 36 times 3z minus the square root of 36. And then for my last one, same drill. The square root of 25 is 5, and the square root of w squared is w. So the square root of that plus 7 times the square root of that minus 7. Okay? And so once again, I hope that you're able to find that this is the factored form of this polynomial. They're equal, okay? This is the same thing as this. This is just what we multiply to get this. That's what factors are. Now, two things that I want to touch on. First off, I always wrote my factors in this order with the plus one first and the subtraction one second. Multiplication's commutative, so I can flip those if I need to. I can write my a minus b term first and my a plus b term second. That's the same thing, okay? So for example, here in this example, I could have written my factors as y minus 5 times y plus 5, and that's the same thing, okay? So the plus one does not have to be first. That's the first idea that I want us to remember. The second one is you gotta be careful because this pattern does not hold true for the sum of two squares. If you have a problem where your square numbers are being added, we can't do this pattern with that. It doesn't work here. So make sure that they're being subtracted. This is the difference of two squares, okay? And so to summarize, if you see this pattern, two square numbers being subtracted, you know that it can be factored by following this pattern right here, and that's going to be true every time.